So this is continuing chapter 20 notes on electrochemistry. So we have what we call two different types of chemical cells. One is called a galvanic cell, and one is called an electrolytic cell. And each one of these are redox reactions, so they are no different than somebody's losing, somebody's gaining electrons. But galvanic cells are spontaneous, and electrolytic cells are not spontaneous. So we are going to start with galvanic cells, and then electrolytic cells is just the flip of it. So we're going to spend most of our time on galvanic cells just because once you understand that, the other one is pretty self-explanatory. So what I have on this page are two diagrams. This is just a general diagram, and then the one on the bottom is more specific as to what elements and solutions we are using. So what you will typically see in a chemical cell, and this is more of a galvanic cell, is I have two containers. And each one of these containers could be a well, it could be a beaker. These are what we call our half cells. And in each one of these half cells, you're going to have a different reaction. So in this container, you're going to have a solution containing a aqueous ionic solution. And then you're going to have a piece of metal that is in the solution. And then this metal is connected through a series of wires. So in this picture, this is showing what we call a voltmeter. And I know if you have physics experience like a multimeter, some way to measure the voltage, you might also see a light bulb in other pictures to show that there is a electricity going through it, so the light bulb goes on. And then on this side, this is also a piece of metal. This is in a solution as well. And then you have this thing here called the salt bridge. All right, so over here on the side, right, at the anode, we have oxidation. At the cathode, we have reduction. And the way I remember it is the A in anode is a vowel, just like ox, the O in oxidation. C is the same as R, okay? So that's how I remember with a setup like this. And again, this is an aqueous solution that these metals are in. So the biggest question mark I always get with these is something called the U-tube, okay? And that is what this is. This salt bridge, so the salt bridge itself, is some kind of mechanism to have what we call an ionic solution free-flowing because we have a buildup of charge on either of the half cells. So there's a purpose to it. What it does is it allows ions to flow between cells without mixing the cells. So we're going to go through this step by step, but it is a very important part to this whole setup. Yes, you need to connect things through wires and the metals need to be there in order to conduct, but we need the salt bridge to connect the two, otherwise it will not work. So we are going to focus on what we call a galvanic cell. Another way you might hear is called a voltaic cell, interchangeable in the world of chemistry. What we're looking at is we are taking a chemical change and changing it into electrical energy. Okay, so we're taking something happening chemically and having it have a electrical charge to it. So the picture you're going to see down here is a specific galvanic cell. It is sometimes called the Daniele cell. And that is because we are using zinc and copper, okay? And I do have a set of videos for you guys to watch on the zinc and copper because it's a pretty famous galvanic cell that we have. So over here on the left, I have a piece of zinc, okay? So realize that this is a piece of zinc metal, okay? in a solution of zinc ions. So this could be zinc nitrate in the beaker, okay? It is then connected to, again, a voltmeter or a light bulb. And over here I have a piece of copper metal. And in here I have some kind of copper solution. It could be any copper solution, but it is copper 2. So this side is my anode. This is undergoing oxidation. On the right is the cathode is undergoing reduction. Now, please note that typically you see on the left is the anode and the right the cathode, but the AP test likes to flip them sometimes. So don't think that that's always the way it has to be, because it doesn't have to be that way. Now, why is zinc undergoing oxidation? Why is copper undergoing reduction? We'll talk about that a little bit later on, or maybe in the next video. I also have what we call a U-tube. This is a glass tube that has a solution in it, ionic solution. So KNO3 is the example they're showing here. And then these are like plugs or some kind of semi-permeable membrane that only lets the ions go through. But you could see that it is touching both solutions so that we don't, we don't get mixing, but they do interact. So I'm going to write down the two reactions over here. So I have zinc becoming zinc ion. So it's losing 2 electrons. Okay, so it's undergoing oxidation. So it's going from a 0 oxidation state to a +2. And then copper is gaining those 2 electrons to become copper metal. So what is happening directly in this situation is zinc is becoming zinc ion. So that's what you see here with the arrow pointing out. Okay, it is essentially becoming more zinc 2+. So what is happening is zinc is losing mass. So if I were to take this piece of zinc metal and mass it before and after this reaction, I would see that the mass would go down. Okay, the zinc ion is increasing in this cell. Okay, while over here you will see the arrow pointing in this direction. So the copper 2 ion that's in solution is essentially plating on this piece of copper. Okay, because you're making more and more copper. So the copper is actually gaining mass. Okay, so if I were to mass that before and after the connection here, I would see the mass would actually go up. The amount of copper solution in there would actually, the copper 2 would actually go down. So here is why we need the salt bridge. I have a buildup of a positive charge over on the left in the anode, and over here on the right, because the copper 2+ is going down, I actually have a lot of NO3 floating around in there without a partner. So what I have is a buildup of a negative charge on the right and a positive charge on the left. So that is why you will see in this diagram that the salt bridge, okay, that KNO3 solution, the nitrate ends up flowing into the left half cell, and the potassium ion flows into the right, so that you have an equaling out of the charges. So the salt bridge essentially alleviates any buildup of charge. That's why it's so very important. So back to this 2 equations, I could write what we call a complete reaction. So zinc plus copper 2 ions goes to zinc 2+ and copper. So this is what we call the net ionic equation. So net ionic equation for a redox reaction. Okay. So this is, again, a pretty common galvanic cell with zinc and copper. Now the question is, why is zinc the one becoming oxidized? Why is copper being reduced? So for this next video that you're going to see, you need to print out what I call the standard reduction table that they used to give you on the AP test. So please print this out, and I will then explain why zinc is undergoing oxidation and copper is undergoing reduction.